Welcome to the latest in our series of webinars that we've done on nitrosamine contamination. With this one, we're focusing on a few techniques that can be applied for detecting unexpected nitrosamine contamination. So ways that you can potentially identify if you've got a problem for things that you might not have been expecting. In a second, I'm just going to hand over to my colleague to take you through to the bulk of the presentation. So I'll just bring him in.
Hello, and welcome to Ellutia's webinar on detecting unexpected nitrosamine contamination. If you have any questions, please enter them in the chat. We'll answer as many as possible at the end. Alternatively, there will be the option to book a call to discuss the problems that you are facing and how we can best meet those challenges together. These will be the topics of discussion. A little bit of history, and then the novel approach to nitrosamine analysis that we take here at Ellutia. So nitrosamines have been studied for many years due to both their prevalence and their carcinogenic potential. Nitrosamines are formed when an amine reacts with a nitrosating agent, and this reaction is catalyzed under acidic conditions or at elevated temperatures. But nitrosamines can also be formed under normal conditions, such as during storage, for example, making not only the detection of nitrosamines, but also the potential nitrosamine concentration that can be formed needs to be assessed. So these are some of the risks that have to be assessed in the pharmaceutical industry, but they can also apply to other industries. Knowing the amine concentrations during the synthesis or as the final product is important, just as knowing the concentration of nitrosating agents present is important. So for a product that does not involve the use or formation of amines, such as aspirin, the risk of nitrosamine formation is minimal. However, nitrosamines can leach from inks or packaging materials, and that must also be considered. The impact of nitrosamine detection and contamination can be catastrophic. Ranitidine was once the most prescribed antacid globally, but it's now been withdrawn from the market due to NDMA contamination. Sartans and metformin are products of concern at the present due to the synthesizing process being likely to form nitrosamines. However, nitrosamines can form in almost every kind of personal care product. Unfortunately, nitrosamines are not limited to cosmetics and pharmaceuticals. They're also found in food, beer, tobacco products, rubber products, and even the air. So how can we screen for nitrosamines? Well, there are two approaches. You can perform a speciated analysis where you look for each and every nitrosamine, or you can use a screening approach to gauge the concentrations of all nitrosamines present, allowing you to quickly release products that show little or no risk. Or at least that allows you to identify which product or products require further analysis. The screening approach gives you increased flexibility, where the same equipment can be used to screen incoming excipients, ingredients, finished products, inks, plastics, and packaging materials. But since there is no chromatography, there's no identification of the exact nitrosamine present. But the throughput is higher than for speciated analysis. The purchase and running cost for a screening approach is also generally lower than that for a speciated approach. Now, such a screening tool has been available from Ellutia, but this was using a manual injection technique. This was what we would call the glassware method. Samples were injected into the reaction vessel where NO is released and then swept to the detector. So this is a dynamic headspace method, but as you can see from the data is still reproducible. Now, these are the chemical reactions that are involved with the screening process. It's split into two parts. The chemical strip reaction is where the hydrobromic acid reacts with the nitrosamine to release NO, or the nitrosyl radical. I might bounce between the two, but when I say NO, I mean the nitrosyl radical. Now, when this enters the TEA, Ellutia's thermal energy analyzer, Now, when this enters the TEA, Ellutia's thermal energy analyzer, the onboard ozone generator reacts the ozone with NO to form an excited state of NO2, or nitrogen dioxide. When this relaxes, it releases a photon of light, and it's this light that is detected. This process has now been automated with the development of the ATNA system, the Automated Total Nitrosamine Analyzer. This is currently being used in the pharmaceutical and cosmetics industries to detect nitrites, nitrates, and nitrosamines. The system gives a molar response for the NO molecule liberated, so any nitrosamine can be detected. The throughput is good, with 6 samples being analyzed per hour, compared with other chromatic techniques where generally you're seeing only 1 or 2 analyses per hour. If you have the likelihood of negative samples, then this shows a quick way of screening through these quickly and cheaply, allowing you to just focus the costly efforts on analyzing the questionable samples. Now, this is a video that summarizes the analysis of a tablet. This is a ranitidine tablet that was analyzed, and this is just to show the simplicity of the technique. So the first step is the grinder sample. You simply want to increase the surface area to volume ratio to have a good extraction. The tablet is then weighed. Solvent is added to extract the nitrosamines. The sample is then centrifuged and filtered. An aliquot of the sample is then transferred to a headspace vial, and reaction mixture is added. So the reaction mixture contains the hydrobromic acid. The samples are then loaded into the sample tray and placed on the instrument. Now, here the sample is vortexed before going into the heated agitator, where the reaction occurs to release the NO. The sample is then vortexed once more to help release the NO into the headspace, before being allowed to cool. An aliquot then of the headspace is injected into the TEA inlet for analysis. We did also perform a 10-fold dilution of this sample so that we would have the concentration within the linear dynamic range for the calibration curve. The ATNA system is sensitive. We're able to detect 1 ppb of NDMA. And as I said earlier, the TEA is a molar detector for the NO molecule liberated. Thus, the sensitivity of 1 ppb of NDMA would equate to 2 ppb of NDELA, as given in the summary at the bottom. This is simply because the relative molecular mass of the NO compared with the rest of the NDELA molecule is about half that of NDMA. The system is reproducible, and as this is an external headspace sampling method, we cannot add an internal standard because we're simply generating NO, and there is no chromatography involved. So an RSD or percent RSD less than 20% is generally accepted. Now, nitrites are also important to study as these are seen to be the main source for the nitrosating agents. Since the nitrate molecule is significantly more stable than the nitrite molecule, then the TE also gives a lower response for nitrates present. So, as can be seen, 1 ppm of nitrite, 100 ppb of nitrite, 1 ppm nitrate, 100 ppb nitrate. So our ratio of recovery is about 3.5% compared with the response from a nitrite. So the ATNA system can screen as low as 1 ppb of NDMA or screen for nitrosating agents in ingredients. But what if there are both nitrosamines and nitrites present? Well, the total NO method, which is what we've been discussing so far, is a gauge for both the current and potential concentration of nitrosamines that could be formed if all the nitrosating agents were to react. However, the ATNC value, apparent total nitrosamine content, is what is typically asked for in the analysis. By adjusting the vial chemistry within the headspace vial, Ellutia has been able to remove up to 10 ppm of sodium nitrite, but still detect 10 ppb of NDMA. This is the calibration curve of sodium nitrite up to 10 ppm. However, this is using the optimized vial chemistry. As can be seen in the raw areas, there is little difference between the area response for a blank containing no nitrite and a sample containing 10 ppm of sodium nitrite. This slide shows that we can easily differentiate between 10 ppb of NDMA from a blank sample and also from a nitrosamine blank sample containing 1 or 10 ppm of sodium nitrite. These are two calibration curves that we have produced. The red calibration curve is up to 250 ppb of NDMA. And the black calibration curves are the same concentrations of NDMA, but the vials were also spiked with 1 ppm of sodium nitrite. So as you can see, the slopes, the intersects, etc. are all very similar. The calibration points are still reproducible. The percent RSDs, the average areas, all the calibration points are all very similar. What does a high ATNC result mean? It means it could indicate the presence of one or more nitrosamines. What are the typical instruments used to perform speciated analysis? Now, the FDA has determined that NDMA can be formed in the inlet liner of GCs, making LC analysis more desirable, though not enforced. However, LC-MSMS is the most expensive of these techniques. MSMS methods can also result in false negatives, and you also need to have standards for every nitrosamine that you wish to detect, simply to ensure that you have the correct retention time, and then daughter and granddaughter ion concentrations and ratios. The GCTEA, however, does not require you to have standards for every nitrosamine present. A sample is injected into the GC inlet, and the oven and the column are used to perform the chromatography, which is the separation of the analytes. The analytes then enter the pyrolyzer, and within the pyrolyzer, heat is used to cleave the NO from the nitrosamines. The NO then enters the TEA for detection. Now, the chemical reactions for the GCTEA analysis of volatile nitrosamines is the same. This second section here is exactly the same. However, we used heat to cleave the NO from the nitrosamine. This is a GCTEA chromatogram of an actual customer sample. This customer has an ATNA system, and they were seeing high total NO and ATNC results. But their LC-MSMS analysis indicated some NDMA and some NMOR, but certainly not at concentrations high enough that would warrant the areas that we are seeing in the ATNA system. This first peak is unretained by the column. This is almost definitely going to be breakdown of a molecule within the GC inlet. From previous work that we have done, we tend to find compounds that contain phenols are prone to breaking down within the inlet liner. And we have a second peak here, which elutes slightly before the NDMA peak. So this could be a 1-methyl group or a 1-hydrogen version of NDMA. It's a possibility. Similarly, we have other peaks that are between standards. So, is this an ethyl propyl instead of a diethyl or a dipropyl? Now, just for reference, this black trace is a 20 picogram on column per analyte injection. So the peak heights we see for 20 picograms under these conditions is about 5 millivolts. And just to give you an idea, that first peak is 1.2 volts. So that's about 250 times higher than the 20 picogram standard. So Ellutia has developed a quick, versatile screening system for screening raw ingredients, solvents, packaging materials, and inks to test for both total NO and for the ATNC value. Armed with this information, you can gauge the potential nitrosamine concentration should all the nitrosating agents present react to form a nitrosamine, as well as the current ATNC value or what the apparent total nitrosamine concentration currently is. Using a screening tool such as the ATNA allows you to test ingredients as part of your incoming QC. Why pay for an ingredient, spend time and money formulating it, only to discover at the end that the batch has an issue? At which point, what do? You spend more money testing to see what's wrong with it, and then disposing of the entire batch. The screening of ingredients allows you to decide whether to use the ingredient for amine formulations or not. Accept the ingredient or reject it and send it back. This also gives you the chance to save time and money. And should you see a high ATNC result, using GCTEA to detect all the viral nitrosamines present, not just those that you have standards for, gives you the greatest confidence that all the nitrosamines present have been detected. This results in more accurate and confident risk assessments prior to product release. Thank you for listening. We have some links and some QR codes here. You can have up to 5 samples analyzed free of charge for a limited time for qualifying customers. So get in touch with us and we'll see what we can do for you. Thank you.
We've got a few questions, bits and pieces coming through. I know we're running close to the end time, so we'll try and get through as many as we can. Any that we can't get through, we will follow up with afterwards. So if you do have any questions about what you've just seen, please, down the bottom of the screen, there should be a Q&A box. If you want to pop them into there, we'll try and get through them, but we'll get started now. So the first question that we had in was, which you kind of touched on, I think, already, but can the system differentiate between nitrosamines, nitrite, and nitrates?
It can differentiate between 2 of those 3 at the same time. So in total NO mode, we can see nitrites, nitrates, and nitrosamines. By adjusting the biochemistry, we can remove the nitrites up to 10 ppm sodium nitrite, leaving you just the nitrates and the nitrosamines. But due to the low response from nitrates, you do have to have quite a significant concentration of nitrates really to interfere. So yes, if you want to differentiate between nitrites and nitrosamines, yes. If you want to differentiate between nitrates and nitrites, yes.
Okay, perfect. The next question was just asking if this approach is suitable for NDSRIs.
Yes, because we are looking for the NO molecule. NDSRIs, or nitrosamine drug substance related impurities, because they still contain the NO molecule, and in the chemical strip reaction, we're using hydrobromic acid to cleave the NO from the nitrosamine bond, absolutely will detect NDSRIs. And similarly for the GCTEA. As long as it either falls apart in the inlet or it's viral enough to go down the GC column, then GCTEA will also detect NDSRIs. Okay.
Next question was, can this technique be used for nitrite determination in drinking water? What sort of sensitivity could be reached?
Nitrites in drinking water, yes. We could detect down as low as 1 ppb of sodium nitrite. Now, I'm being careful with what I say here. I'm listing the nitrites that we have tested and the concentrations that we get to because, as I said, we are a molar detector for the NO molecule. So 1 ppb of sodium nitrite would equate to be 2 ppb of a nitrite that is twice the molecular mass of sodium nitrite. So yes, nitrites in drinking water, yes, you can use it for that.
Okay, the next question was another nitrite question. How does the system differentiate from organic NO2 species present?
We're detecting all nitrites. I'm assuming we're talking just nitrites here. For example, if your material contains nitrocellulose, then you're looking at an organic nitrite. The risk of nitrosamine formation during storage is just as important with organic nitrites as what it is from inorganic nitrites. And because of the stability of the nitrite molecule, it doesn't matter if it's organically or inorganically bound. It will all be based on the nitrite bond strength.
Okay, perfect. I know that we're basically coming pretty much, we're just running over time at the moment. So I'll ask one more question and then there's quite a few other ones. So what we'll do is we'll follow up with all the other questions that people have asked post the event with everybody. So the final question we've got here that I'll ask is a question regarding the in situ formation of nitrosamines within the headspace of the ATNA analyzer that might lead to false positive results. Studies have shown that headspace of the GCMS resulted in false positives due to in situ formation of nitrosamines from the heat within the headspace. So how does that affect with the ATNA?
Because with the ATNA, we're looking at a chemical reaction. So you've got amines, nitrosamines, and nitrites. The HBO will cleave all the NOs, so you will see both the nitrite NO and the nitrosamine NO. However, with the optimized vial chemistry, that is able to eliminate the NO from the nitrites from the nitrosating agent itself. So any amines present in the sample will not have the NO from the nitrite to form a nitrosamine, therefore release the NO. Now, also, I think you're kind of comparing apples with pears in that I think you're talking about a speciated approach to analyzing your sample via headspace. At which point, yes, if you do have nitrites, amines, and nitrosamines in your headspace vial, then as we said earlier, acidic and elevated temperatures can catalyze the formation of nitrosamines. And if you're then using static headspace or something like that to transfer into an MSMS, then yes, you can get the formation of nitrosamines to be detected. So the chemical strip reaction, no, you wouldn't see that same interference because the cleaving is happening instead of the reaction. And similarly, with the GCTEA, you do have a solvent extraction of your sample, and then that is simply injected.
So we've got quite a few other questions still lined up, which as I said, what we'll do is we'll go through post-event and we'll respond to everybody. I've taken a note down of all the questions and who asked them. So we'll go through afterwards and answer all those questions where we can. So once again, thank you to everybody for attending today. We appreciate your time.
Can I just make one caveat? Sorry. So that last question about headspace analysis. Now, obviously, if you're using GCTEA and performing the same headspace analysis, so this is a sort of yes, then under that circumstance, then yes, your vial chemistry in effect is causing the formation of the nitrosamines. So yes, GCTEA would see that same issue because it is then able to detect a nitrosamine present, whereas nitrites generally don't go down the GC columns. So the ATNC wouldn't have a problem. GCTEA with liquid injection wouldn't have a problem. But if you tried headspace analysis, you have generated nitrosamine yourself and the detector is simply detecting it. Sorry, just needed to clarify.
Yeah, no, good. Thank you for doing that. So again, just thank you to everybody for attending today. What we'll do now is post this webinar is finished. We'll send out an email in probably an hour or two with a link where you can download the slides. We'll put up a copy of this video again, so if you want to go back and rewatch any of it, you will be able to. And we'll also include a link there where if you want to look to have some samples tested, there'll be a link there where you can book a call to have a chat about your samples, and we can look to get some samples run for you so you can see how this kind of approach might work for your organization. So once again, thank you everybody, and we'll hopefully see you on another webinar soon. Bye bye.